9.1 is a section that talks about compound inequalities. So basically what we're doing is we're building off of the concept of an inequality. So I like to start, obviously we have been very familiar with the concept of equality or equations. We've been using them for most of the textbook. And occasionally we've been talking about inequalities. So if I had for example, if I had x plus 3 equals 7, the very fact that I'm using an equal sign, I am talking about an equality. And I know this may be a little dumbed down for most of you 9.5 and 9.6 students, but for those of you who are just getting back up to speed, it's nice to talk about these things. So just by virtue of the fact that I'm using an equal sign, what I am really doing is I am solving an equality here. Well, an inequality is just something that isn't equal. It's either going to be greater than or equal to, it's going to be greater than, or it's going to be greater than or equal, or it's going to be less than, or it's going to be less than or equal. Those are the only options for an inequality. So I could just as easily turn my original equality, x plus 3 equals 7, I could turn that into an inequality just by changing the sign. If I wanted to say that x plus 3 was greater than 7, that's the symbol I would use. If I wanted to say it was greater than or equal to, I would just write the equal sign underneath it, or half of it. And then if I wanted to say that it was less than, I would use the left-bound arrow. And then less than or equal, I would just put the equal sign under there. Try to think of it when you're seeing these on tests and you get stuck about, well, does that symbol mean greater than or equal? I like to think of it as a mouth. You know, if the mouth opens up or a megaphone opens up, the sound that's on the open side, on the bigger side, is bigger. You know, so think of like if you're blowing through a megaphone, that sound out there is going to be bigger than the sound on this side. So whichever the direction is facing the megaphone, that big side is the bigger number. So 7 is bigger than this quantity, which another way of saying is x plus 3 is less than this bigger number. Okay? Hopefully that helps. So as we continue to talk about compound inequalities, what we mean is to say we're going to put more than one equality or inequality together. We're going to combine them. You can kind of see it in the word there. We're going to compound them together. And when we do this, we can do this in one of two ways. We can say that we have a compound inequality that means a quantity is between two values, or our inequality exists in one set that is lower than a value, or in another set that is greater. So what do these words really mean? In order to talk about this, and this is what's so interesting about working with compound inequalities, is we finally get to start talking in more depth about set theory. And I'm not going to give you a whole lecture on set theory because I don't know enough of it. But I find the subject fascinating because we talk about numbers on a number line, and we talk about various ways to work with numbers, but for the first time, now we start to work more regularly with sets. And all sets are groups of things that we have in common. So you'll start seeing notation for sets when we start talking about compound inequality. And so I think it's probably useful to start talking about what kind of set notation, what those symbols mean. But we'll probably need some examples to work with in order to visualize it. So let's build our first compound inequality. And I'm just pulling these off the top of my head and then solving them. There are plenty of examples in your book that you can refer to, but the method is exactly the same. So I'm going to say that my first inequality is x is less than or equal to 3. And then I'm going to say, and x is greater than or equal to -7. I have the key word here, and. So what I'm really describing is a group of numbers that are less than 3 and greater than -7. So if I were to draw this visually on a number line, and I wanted to find out where all those suspects lived, I know that they have to satisfy both conditions. Because you would agree that, let's say I come up here to 3. I can find numbers that are less than or equal to 3. They're all these numbers. They're all the numbers including 3, and that go all this way out to -infinity. Those are all the numbers that satisfy the first condition. But that's only half of what I'm looking for. My compound inequality tells me that I have another condition to meet, which means I have to find the numbers that also satisfy the fact that they are less than or equal to -7. So I come down here on my number line, -5, -6, -7, and I have to say, well, this is where my second condition lives. All my numbers, if I was just looking at all the numbers that satisfy the second condition, well, I would have to include all the numbers that start from -7 and go all the way up to positive infinity. But the numbers that meet both requirements live inside here. They're all the numbers between -7 and 3. And you can kind of see visually why that's true. I can't have -8, for example, as one of my solutions, because -8 is certainly less than or equal to 3, but it's not less than -7. Well, it isn't. It's not greater than -7. That's what I should say. Negative numbers, the value gets bigger, but the representation of them gets smaller, so it gets a little tricky. Anyway, so that's a good example of an and compound inequality. Now I'm going to change the same compound inequality, but I'm going to change the word. I'm going to change it from and to or. Will this change our result? I can't hear you, but the answer is yes. Yes, it will. You're right. Some of you are right. Others of you are wrong. That's okay. So we'll make one little change, but one significant change. Now I'm looking for answers that satisfy both of these conditions. Okay? So when I put my number line together, and same approach. Let me start with my first condition. So all the numbers that satisfy the fact that they are less than or equal to 3 are all those numbers in that direction. Okay? And then all the numbers that satisfy the second condition, 6, -7's there, are these numbers that go in this direction. Well, what I'm saying is that either x satisfies this condition or x can satisfy this condition. So really, am I excluding any number? Doesn't every number on the number line satisfy either one of these conditions? Now, I'm not saying, it's not like I'm at a restaurant asking you, or telling you that you can have either soup or salad, but you can't have both, right? I'm saying you can have soup, or you could have salad, or you could have both, okay? This is called an inclusive or. It means it can be in either camp or it can be in both camps. So my solution to this one is all real numbers. Or if we were to use interval notation, we would say the numbers that go from -infinity, that start at -infinity and stop at positive infinity. We'll get back to interval notation in a second. And if I were to use set notation to describe this number, I would call this the set. We use curly brackets for set. The set of all x such that x is between -infinity and positive infinity. Another way to write this would be the set of all x such that x is a real number. And now you're starting to see some of the translation that we do. Not all of mathematics is simple. Some of it relies on words to describe what's going on. So this is one of those cases where this is a perfectly acceptable mathematical answer. All right, so let's work a little bit more with some of this compound inequality, and let's talk about set notation for a second. Because what I can do is let me work with a different example too. Now I'm going to write a compound inequality that is an AND inequality. We'll call it an AND inequality. And inequalities can always be rewritten in compound notation, if you'll give me the license to call it that. So our previous example was x is greater than or equal to 3, and x is less. Did I say that right? I think it's x is less than or equal to 3, and x is greater than or equal to -7. That's what we had. We can rewrite this, because it's an AND inequality, we can rewrite it with just one x. So we say x is between our two numbers. And obviously we have to put, well, it may not be obvious. We start with the lowest number we say -7. We say that obviously that number is going to be lower than x, and x is also going to be lower than our number here. Have we said the same thing? X has to be less than or equal to 3. Well, that's true. We have that part. And x has to be greater than or equal to -7. Well, x is on the open side of the mouth this time. It's on the loud side of the megaphone. So it is bigger than -7. So this is, and you'll see both versions of these in your homework and possibly on your test. I don't know how to write them. But this is the same thing as an AND equality. They can be rewritten. And our solution set is the same set that we had last time. Remember, it was all the numbers between. Well, this is the answer, right? Written like this, you can see what the solution is. It's all the numbers between -7 and 3. Okay. So if we were to make this a little bit more complicated, let's use a different example. Let's say I want to know what values of x will solve this compound inequality. Say 1. Now obviously I know that -10 is less than 1. So I'm going to have solutions that exist inside this inequality. So how would I solve this inequality for x? And once I find that solution, how do I express that in mathematical terms? Well, the good news about compound inequalities is you can either choose to split them up as two equations, or you can treat it like a super equation, where just like if we had just this equation and we did something to one side, we'd have to do it to the other side. It's the same kind of principle, only now we have 3 sides. But if I do something to this side, I have to do it to the middle and this side. But same kind of operations, right? So what I'm going to do, I'm going to get x all by itself by subtracting it from all sides. Okay? -10 minus 5 is going to be -15. And I keep my signs. And now I have +5 minus 5 is going to get me 0, so I just have 2x in the middle. And then 1 minus 5 is going to get me -4. Notice that I keep my signs, my inequality signs exactly the way that I had them before. Now the same thing that I would do if I had an equality, I'm going to do here. I want x all by itself because I'm trying to solve for x. So in order to get x all by itself, I'm going to divide everything by 2. Dividing all sides by 2, I notice that I get my 2x to cancel, and I'm just left with x. That's what I wanted. My right side, I get -4 divided by 2, which will get me -2. And then I get a really nasty fraction. Well, not the nastiest fraction we've seen, but Yeah, not my favorite fraction. Oops. And we get negative 15 over 2. So I've done it. I've solved my inequality, and I've identified my solution set. Now, there are two ways to write that solution set. So if I had just an equality or just an inequality, a single inequality, this is okay. We can say that x is less than or equal to 7, and then we could write it in either set builder notation, or we write it in interval notation. And I will describe what both of those look like. These are our notations. You'll have to be careful because some professors prefer set notation and some professors prefer interval notation. So be very careful when you're working through these examples. It will tell you what terms it wants its answer in. So if I wanted to rewrite this isolated solution in the correct notation, what I would say, if my professor said, you need to express this in set builder, I have to remember that set builder starts with the curly brackets. And what I'm saying is the set of all x, so this is, I'll make my English translation. The set of, this is all x, this line represents such that, and then basically just take your condition and put it right in here. I like set builder notation because it's the easiest. Such that x is between negative 15 over 2 and negative 2. And then I got to close my brackets. That's set builder notation. Okay? Easy. If you understand what the terms mean, then you can translate it very easily in your mind. Interval notation's nice too. It's more visually based, I think. And it's going to require that we introduce a couple of new symbols. And we'll do that in a second. For this answer, I have just the bracketed interval where it starts from negative 15. When you're building interval notation, you always start with the lowest number. You move from lowest to highest number. It's interval from this number to this other number. And we go from low to high. So again, and this is set up correctly because negative 2 is negative 4 over 2, which is still bigger than negative 15 over 2. So we're in the right direction. And then I have to talk about the brackets. Why am I using brackets and why am I not writing it this way? Why am I not using parenthesis? This has everything to do with the nature of our symbol here. So and this will be the symbol in your original setup, all right? If you have, this means less than or equal to. It has two options. This also means less than or equal to. Anytime that you have an or equal, that means you have to include the value that you find in your results. Because this is saying negative 15 over 2 is a valid answer. If you were writing this as an expression on the number line, you would say that, let's say this is negative 2 and this is negative 15 over 2. We have to include this, so we fill them in because we know they're valid points. If I had, this interval goes from less than or equal to x, but I'm not including 2, it's less than negative 2, then the way that I would mark that on my number line is I would draw a circle around it. Every point up to, but not including. So, and then I would fill in my interval here. This is the visual representation of the interval that I'm describing. But you can't just show your professor a picture of the number line. You have to write it in more mathematical terms. That's what we like. So what we say is that if we are including a number, we use brackets, okay? And if we are excluding, we use parenthesis, okay? If I need to include a number, like if I'm trying to write this visually, I know that I'm including this number, but I'm excluding this. Then I make sure that I use my left bracket for my include here and my right parenthesis to exclude my number. That's how you would write that in interval notation. Okay. In our original solution, though, we just had two things that we needed to include. So our interval looks like this. Interval notation looks like this. Okay. Just go ahead and I'll give you a tip. I started out with and inequalities because the solutions to and inequalities will usually be one interval. Okay. X will always be between two numbers, and you can always write that as one interval. Okay. Or inequalities are usually very different, as we'll see here in a second. In fact, I can't solve, any compound inequality that I write where some expression of x is between two numbers. I cannot rewrite this as an or inequality because I'm not saying it's an or equality. What I'm saying is that both these conditions must apply. So the way that we translate this is that this is an and inequality. I'm saying 2x, let me put numbers in here. So let's see, I've got negative 20, and let's say I've got 30 over here. So what I'm saying is this quantity of x is greater than negative 20, and this quantity of x is less than 30. So I can rewrite this compound inequality as two separate inequalities using my and. This would look like 20, 2x plus 3, and 2x plus 3 is greater than or equal to 30. And then I could go from there. I could solve both for x. And every time I'll end up with an interval that's bound because I'm dealing with an and inequality. So with an or inequality, there's no way to write them with only one expression of x. You'll always see them as 2x plus 6 is greater than or equal to 0, or 2x, well, let me use a different, 5x minus 3 is less than or equal to negative 3. Let me say 30. There we go. I'm making this, I don't even know if this has a solution. We'll find out. But these will always come to you in two pieces because there's no other way to write them. Okay? So we're going to solve each piece. That's the unfortunate thing. So solving for the first piece we get, let me do this. I will subtract minus 6 from both sides, and I'm left with 2x is greater than or equal to negative 6. And then dividing both sides by 2, I get x is greater than or equal to negative 3. Totally valid for the first piece. And then what I'm saying is, and now I'll solve this side by adding 3 to both sides, and I get 5x is less than or equal to negative 30 plus 3 is going to be negative 27. And then dividing both sides by 5, I'm saying that x is less than or equal to negative 27/5, which is just slightly less than, or slightly bigger than negative 4. This is written as a mixed number would be negative 5 and 2/5. So less than 5. So now I'm saying that a number can be, so on my number line, I'm saying a number, in order to satisfy this or inequality, it must be greater than or equal to negative 3. So if this is 0, met negative 1, negative 2, negative 3. So this is where the first piece lies, and judging by my sign, I have to include this. And I'm saying that it is greater than, right? This is the louder side of the megaphone, so it goes this way. Okay, that's the first piece. And now I'm saying, well, my numbers also have to be less than negative 5 2/5. So I'm at -3 here, -4, -5, -6. So I'm somewhere in between here. And then, judging by my sign, I'm also including it. And then I'm saying that they're less than, so those numbers keep going in that direction. All right? Well, when I fill in my number line here, because what I'm doing is I'm looking for solutions on the number line. I've got this number line here, and then I have this gap. These numbers don't satisfy this inequality. They're not in either one camp. And then I come back to -3 and I get the rest of my solutions. Sometimes this happens. Sometimes you get a gap. Well, how are we going to write a gap in math terms, right? So in set builder notation, you would write the set of all x such that x is greater than or equal to 3 and, or x is less than or equal to -27/5. Set builder notation is easy because you just translate what you found in Mathese and just stick it between some fancy brackets, add a little line and an x. You're done. Interval notation, you just have to keep working. So we start with our first interval here, and we note that those numbers go all the way out to -infinity. So, and anytime that we have an interval that goes all the way out to -infinity, we use an exclusion bracket because infinity, we don't have a definite value for negative or positive infinity. So we say that we include it just to let math professors know, hey, we know it's not a real number, or it's not a number that we have gotten to yet and probably won't get to. So let's say, so we have to exclude -infinity, but based on our sign here, we have to include, I'm sorry, we're talking about this interval over here. We have to include -27/5, so we use the brackets. And now describing this interval here, I'll just drop down, we'll have to include our -3, and these numbers go all the way out to positive infinity. So again, we exclude. Now, I have to explain that they're in either this group or they're in this group. And the way that we say that is that they are in union. We use this fancy, broad, it looks like a capital U, but it's really just like an open-facing parabola. All right? Big ol' U for union. So let me go ahead, and this gives us a good opportunity to talk about set notation, and it's probably a good place for us to break.